Earthquakes, the sudden shaking of the Earth's surface, are natural phenomena that have fascinated and puzzled humanity for centuries. These seismic events result from the dynamic processes occurring beneath the Earth's crust. Understanding the causes of earthquakes involves delving into the intricate movements of tectonic plates and the geological forces at play. Tectonic plate movements. The Earth's lithosphere is divided into several large tectonic plates, each bearing the Earth's continents and oceans. These plates are not static. They are in constant motion, driven by forces generated within the Earth. The primary cause of earthquakes lies in the interactions between these tectonic plates. Divergent boundaries. At divergent boundaries, tectonic plates move away from each other. This movement creates gaps, allowing magma to rise from the mantle and solidify to form new crust. The stress and pressure associated with this process can lead to seismic activity. While earthquakes at divergent boundaries are generally less intense, they contribute to the overall seismic activity on Earth. Convergent boundaries. Convergent boundaries witness tectonic plates colliding or moving towards each other. Subduction zones, where one plate is forced beneath another, are common examples. When an oceanic plate subducts beneath a continental plate, the intense pressure and friction generate powerful earthquakes. The release of accumulated stress along the subduction zone can result in seismic events with significant magnitudes. Transform boundaries. Transform boundaries involve plates sliding past each other horizontally. The friction between the plates prevents smooth movement, causing stress to accumulate. When the stress exceeds the strength of the rocks, it is suddenly released, leading to earthquakes along fault lines. The San Andreas Fault in California is a well-known example of a transform boundary that has generated destructive earthquakes. Human-induced earthquakes. While natural tectonic processes are the primary drivers of earthquakes, human activities can also induce seismic events. Activities such as mining, reservoir-induced seismicity, due to the filling of large dams, and hydraulic fracturing, fracking, for oil and gas extraction can alter the stress distribution in the Earth's crust, potentially triggering earthquakes. In conclusion, earthquakes are a consequence of the dynamic and ever-changing nature of the Earth's crust. Tectonic plate movements, whether divergent, convergent, or transform, play a crucial role in shaping the Earth's surface and generating seismic events. Understanding these geological processes is essential for mitigating the impact of earthquakes and enhancing our ability to live harmoniously with the dynamic forces of our planet. What is earthquake engineering? Earthquake engineering, a specialized field within civil engineering, is dedicated to understanding, predicting, and mitigating the impact of seismic forces on structures in the built environment. As earthquakes continue to pose significant threats to communities worldwide, earthquake engineering plays a crucial role in developing resilient infrastructure and safeguarding lives and property. Seismic hazard assessment. One of the fundamental aspects of earthquake engineering is seismic hazard assessment. Engineers use sophisticated techniques to evaluate the seismic activity of a region, considering historical seismicity, fault lines, and ground conditions. This assessment informs the design and construction of structures to ensure they can withstand potential earthquake forces. Structural dynamics and design. Earthquake engineers focus on the dynamic behavior of structures during seismic events. They employ principles of structural dynamics to analyze how buildings and bridges respond to ground motion. Based on this understanding, engineers design structures with features like seismic-resistant materials, base isolators, and dampers to minimize damage and ensure the safety of occupants. Building codes and regulations. Earthquake-prone regions often have stringent building codes and regulations developed by earthquake engineers. These codes dictate construction practices, materials, and design parameters to enhance the seismic resilience of structures. Compliance with these codes is critical for minimizing damage and loss during earthquakes. Innovative technologies. Advancements in earthquake engineering have led to the development of innovative technologies aimed at improving seismic resilience. Base isolation systems, for example, allow buildings to move independently of the ground motion, reducing the transfer of seismic forces to the structure. Engineers also employ advanced monitoring systems to assess structural health and detect potential vulnerabilities over time. Education and research. The field of earthquake engineering thrives on continuous education and research. Engineers and researchers explore new methodologies, materials, and technologies to enhance seismic resilience. By staying abreast of the latest developments, earthquake engineers contribute to the ongoing improvement of design practices and construction standards. Emergency preparedness and response. earthquake engineers collaborate with emergency response teams to develop strategies for mitigating the impact of seismic events. This includes planning for evacuation routes, designing earthquake-resistant shelters, and implementing early warning systems to provide residents with crucial seconds to seek safety. In the face of the persistent threat of earthquakes, earthquake engineering stands as a vital discipline dedicated to ensuring the safety and stability of our built environment. Through meticulous assessment, innovative design, and ongoing research, earthquake engineers play a pivotal role in creating structures that can withstand seismic forces and contribute to the overall resilience of communities around the world. What can be done as a precaution against earthquakes? Earthquakes pose a significant threat to communities, making proactive measures crucial for minimizing their impact. Firstly, adhering to and enforcing stringent building codes and standards is paramount. Constructing earthquake-resistant structures with reinforced foundations and flexible building materials can significantly reduce the risk of collapse during seismic events. Additionally, implementing seismic retrofitting for existing structures helps fortify buildings and infrastructure, enhancing their ability to withstand the forces generated by earthquakes. Another key aspect of earthquake preparedness involves educating the public and fostering a culture of awareness. Communities should conduct regular drills and awareness campaigns to ensure residents are well informed about earthquake safety measures. This includes teaching individuals the proper response actions, such as drop, cover, and hold on, and encouraging the creation of emergency kits containing essentials like water, non-perishable food, first aid supplies, and important documents. Furthermore, investing in early warning systems is a crucial step towards mitigating the impact of earthquakes. These systems can provide advance notice, allowing individuals to take cover, emergency services to prepare, and critical infrastructure to initiate automated shutdown procedures. By combining these measures, from construction practices to public education and advanced warning systems, communities can take substantial steps toward reducing the vulnerability and enhancing the resilience of their residents in the face of seismic events. Notable earthquakes in recorded history. Great Chilean Earthquake, 1960. The Great Chilean Earthquake, occurring on May 22, 1960, holds the record for the most powerful earthquake ever recorded. With a magnitude of 9.5, it struck off the coast of Chile, generating tsunamis that affected coastal regions as far away as Hawaii, Japan, and the Philippines. The seismic energy released during this event was staggering, highlighting the immense forces at play along tectonic plate boundaries. Alaskan Earthquake, 1964. On March 27, 1964, the Prince William Sound region of Alaska experienced a massive earthquake with a magnitude of 9.2. This event ranks as the second most powerful earthquake in recorded history. The seismic activity triggered tsunamis, landslides, and widespread ground shaking, causing significant damage in Alaska and beyond. Indian Ocean Earthquake and Tsunami, 2004. The Indian Ocean earthquake on December 26, 2004, had a magnitude of 9.1-9.3. The undersea megathrust earthquake generated a devastating tsunami that affected the coastlines of several countries surrounding the Indian Ocean. The tragedy resulted in widespread loss of life, making it one of the deadliest natural disasters in recent history. Japanese Earthquake and Tsunami, 2011. The Tohoku earthquake, which struck off the coast of Japan on March 11, 2011, had a magnitude of 9.0. The earthquake generated a massive tsunami that inundated coastal areas, causing extensive damage and triggering the Fukushima Daiichi nuclear disaster. This event emphasized the importance of comprehensive preparedness and early warning systems. These historical earthquakes underscore the immense power of tectonic activity and the need for robust seismic preparedness. While advancements in earthquake engineering and early warning systems have improved our ability to mitigate the impact of such events, understanding the lessons from these powerful earthquakes remains crucial for building resilient communities in earthquake-prone regions.